Welcome, students. Today we're going to look at an introduction to hyperbolas. Hyperbolas are the last type of conic section that we're going to be looking at. So let's take a look at a definition, a graph, and we'll dive in. So a hyperbola is the set of all points for which the difference of the distances from two fixed points called the foci is a constant. What that means is that if we look at a point like this one P on the hyperbola, the difference of the distances between P and the one focus and the other focus, so the difference of these distances remains constant. So if we were to pick a different point over here on the hyperbola, we would have different distances, of course, but the difference of those distances would be the same as the difference of these distances. Now, hyperbolas have two branches, one on one side and one on the other side, because if we look at a point on this side, kind of the mirror image of this other point, we would have the same two distances, just reversed, and the difference of those is the same as the difference of these. So hyperbolas, unlike our other conic sections, have two different branches, and these are going to continue outward. So the graph that we have here is only a portion of the parabola. Now, I'm not going to go through all of the calculations here like we did with ellipses and parabolas to figure out what the equation of a hyperbola is going to be, but I will just give you a little bit of a skeleton idea of how the equations are made, and then I'll show you the exact form of an equation. So we know that the difference of the distances is going to be some constant. So basically the distance from our point P to focus 1 minus the distance from point P to focus 2 is going to be plus or minus. The reason we say plus or minus is because we don't know which one is larger. We can have either one being larger. So the difference might be negative, it might be positive. And we're going to make this a 2a. We know that the difference has to be a constant. We're going to choose 2a here, just like we chose 2a to be the sum of the distances with an ellipse. And the reason we do that is simply because it makes the math work out a lot more simply when we set up our equation. So if we do this, and we know that the coordinates for these points are x comma y, c comma 0, and negative c comma 0. And if we also take b squared to be c squared minus a squared, which is a little bit different than we had with an ellipse, but it's, again, going to be the kind of substitution that we make that makes things look a lot nicer. If we do this and we go through all of the calculations using the distance formulas and the coordinates for these points and multiplying everything out and canceling terms that can be canceled and making this substitution, we will end up with an equation in the form x squared over a squared minus y squared over b squared equals 1. So this is the equation for a hyperbola that is centered at the origin and has foci at c comma 0 and negative c comma 0. And we recognize that it looks very similar to the equation of an ellipse, except with an ellipse it would be the sum of these two terms, and with a hyperbola it's the difference, which shouldn't be too surprising or too crazy, because when we were looking at an ellipse, we had the sum of two distances being constant, and now that we're looking at a hyperbola, we have the difference of two distances being constant. So it works out very similarly. A lot of the math is very similar, and we end up with a difference here instead of a sum. Now, because the way that this hyperbola exists in two pieces, and these two pieces are kind of opening to the right and opening to the left, notice that we have x-intercepts, but we do not have y-intercepts. Now, if we wanted to find the x-intercepts, we would let y be equal to 0. So this term would vanish, and we'd have x squared over a squared equals 1. And for x squared over a squared to be equal to 1, the numerator and denominator would have to be the same. And in that case, x would have to either be a or the opposite of a. So the x-intercepts are going to be at plus or minus a, comma 0. So let's write that out. The x-intercepts are going to be at plus or minus a, comma 0. And we call these the vertices of the hyperbola. These are the points that are closest together on the two branches of the hyperbola. There are no y-intercepts. If we tried to find the y-intercept, we'd have to let x be 0, and this term would vanish, and we would have negative a perfect square equals positive 1, and we know that if we square something, it's going to be positive, and we take the opposite, it's going to be negative. So there is no solution to that equation, which is why we will have no y-intercepts. So again, we have this hyperbola. It's split into two branches. We've got one focus for each branch, and then the points that are closest to each other are called the vertices. They are at plus or minus a, comma 0. And we can call the line segment that connects the two vertices the transverse axis. So let's write that out here. The transverse axis is the line segment connecting the vertices. We probably won't use that vocabulary too often. We might have a couple of homework assignments that ask for the length of the transverse axis, but it's not the most important piece of vocabulary. Understanding the vertices and the foci are much more important. Now, this is a hyperbola whose two branches open to the left and to the right. We can also have a hyperbola whose branches open upward and downward. And we're going to take a look at that a little bit more in the next video, along with some other properties of hyperbolas.